Today, we're diving into the invisible magic that powers our entire connected world, wireless communication. Let's get right into it.
So, have you ever stopped to really think about it? I mean, how does your phone, this little thing in your hand, talk to a cell tower that could be miles away, instantly, with absolutely no wires? Well, the answer is hiding in plain sight, in a kind of invisible rainbow of energy that's all around us right now.
This hidden world, it's called the electromagnetic spectrum. And you can think of it as the invisible highway that all our wireless data, every text, every video, every call travels on. To really get how your phone works, we first have to understand this amazing fundamental force of nature. So, what is it exactly? Well, the electromagnetic spectrum is basically the full range of all possible electromagnetic waves. Imagine a rainbow, but instead of just 7 colors, it has countless colors our eyes can't see. And they're all organized by their frequency, which is just how many waves zip past a point every second. And the craziest part? They all travel at the speed of light.
All right, let's take a look at the lineup. On the very low end, we have radio waves. And as we move up that spectrum, the energy gets higher, we hit microwaves, then infrared, and then that teeny tiny little slice that we can actually see, visible light. Keep going and you get into the really high energy stuff, like ultraviolet, X-rays, and all the way up to gamma rays.
And here is the single most important rule of the entire spectrum. You gotta remember this one. The higher the frequency of a wave, the more energy it has. It's that simple. So a low-frequency radio wave is kinda gentle. It can travel a long way. But a high-frequency gamma ray, it's incredibly powerful. This one relationship is the key to, well, everything else we're gonna talk about.
Okay, so with this huge menu of waves to choose from, which ones are the real workhorses? Which ones do we actually use to carry our calls, our Netflix streams, and our cat videos? Turns out, only a couple of them are really right for the job.
First up, we've got radio waves. Now, I want you to think of them as the marathon runners of the spectrum. They're not necessarily the fastest, but boy, they have incredible endurance. They can just go and go and go.
And here's why they're so incredibly reliable. Their low frequency means they can travel for miles, and get this, they can easily pass through stuff like buildings, walls, and trees. That makes them absolutely perfect for creating that wide area coverage we depend on for things like 4G, our home Wi-Fi, and even broadcast radio.
But what if you need pure, unadulterated speed over distance? Well, that's where our second workhorse comes in, millimeter wave, or what everyone just calls MM wave. So if radio waves are the marathon runners, MM wave is the Olympic gold medal sprinter.
See, M waves have a very high frequency, and that lets them carry massive amounts of data at unbelievable speeds. This is the secret sauce behind 5G. But, and this is a big but, here's the trade-off. That same high energy makes them awful at getting through obstacles. A wall, a window, even your own hand can block the signal. They are built for speed, not for endurance.
Putting it all side by side really makes it clear. For long range and good penetration, like with our 4G networks, we need radio waves. But for crazy high speeds over short distances, like in a dense city with 5G, we need M wave. It's the classic tortoise and the hare situation, right? And the thing is, to have a complete working network, we absolutely need both.
You know, this brings up a pretty good question. What about all those other waves we saw on the spectrum? Why can't we just use, infrared or even X-rays to send our data?
Well, the reasons are actually really simple and practical. Infrared, invisible light, they get blocked by walls, easily. Your phone wouldn't even work in your pocket. And as for X-rays and gamma rays, yeah, they have way, way too much energy. They'd be seriously dangerous to our health. So for communication, those are a definite no-go. So all of this, it all leads to this one core principle of wireless engineering. It's not about finding one single perfect wave. It's all about striking the right balance in a fundamental trade-off. You see, every single wireless system is a compromise between these 3 pillars. There's coverage. How far can the signal actually go? There's data rate. How fast can we send the information? And then, of course, there's safety. Is this wave safe to be around all the time? Engineers have to constantly juggle these priorities. Do you need broad coverage for a rural town? Or do you need insane speed for a packed stadium? And always, it has to be safe.
So if you take away just one thing from all of this, let it be this. When it comes to the physics of wireless, you just can't have it all. It is always a trade-off between coverage and speed.
The waves that travel the farthest carry the least data, and the waves that carry the most data, well, they travel the shortest distances. That's just a fundamental law we have to work with.
And that leaves us with a really fascinating challenge for the future, doesn't it? Our world's demand for data just keeps growing. It's insatiable. So as we keep pushing the boundaries, what's it going to be? What do we prioritize? Are we going to build more and more towers, a denser network to shrink the distances? Or will we find some new way to push the speed limit even further? That's the puzzle engineers are trying to solve as we speak. Thanks for watching.